All right, thanks. So I made a last-minute decision to turn this from a 30-something slide talk into about 5 slides and a live demo. So there's every possibility this could go pretty bad. So please bear with me. But thanks for the intro. I guess I'm Peter. I work for a company called Upwind Security. We are primarily a runtime security platform that has also more recently started looking into shift left as well. I have worked in tech for 20 years. My primary interest is Linux. I am an engineer and manager, but don't hold that against me. I very much still consider myself a software engineer. The goal of this talk is really simple. I think we're all nerds, right? I love computers. You guys love computers. We can be friends. This is one of my favorite toys to play with. eBPF is an extremely powerful piece of technology that can allow you to build really cool monitoring and security performance applications with Linux. So I'm really happy to hopefully share with you an example of how you can do that today. And what I'm going to do is start off with like a premise and show you how to take what is quite a simple idea the whole way through into execution. So we need a target, like a story to chase. If we're going to take an idea and go and build something, we need some guardrails to keep us focused. So I thought everybody likes to feel a little bit naughty, right? Even the whitest of white hats amongst us can get our kicks by feeling a little like a black hat now and again. So I thought, what is a really well-known piece of software that a lot of us use day to day that we can try and extract some information from? And OpenSSH came to mind. It's a wonderful piece of technology. What I'm showing you today isn't a vulnerability, but hopefully the fact that it's familiar will help resonate the power of eBPF. I should also say that in my company, we use eBPF a lot. We use it so that we can help customers understand exactly what is running in very large clusters at runtime. We aggregate information about process and network information in a way that does not negatively impede performance. So it is close to my heart personally and professionally. So before we get started, a quick glossary of terms. So we're going to talk about probes today. Probes allow for the insertion of code in an application's user space or kernel space. And if that doesn't make too much sense right now, hopefully by the end of this talk that'll be super clear. We're also going to use eBPF, which really just allows us to attach programs to run processes at runtime without needing to restart them or modify kernel code. A quick side note, just as the previous talk shilled Rust a little, I'm a big shill for Docker. It is a fantastic debug environment to set up, and as part of this talk, we also have an open source repository on my GitHub, which I can show you here. So if you do find that during this talk you maybe miss a step or two things you can't really connect two different points, you can just go and grab this whole repository, which includes the Docker image, and hopefully start playing about with it locally. PR is very welcome. On Docker, really all we're doing is grabbing the Ubuntu 2204 image. We're installing OpenSSH server from the default apt source. All we're really doing configuration-wise is making sure that the root user has a password so that we can log into the SSH server, and we're also permitting root login. You do not need root login to do what we're about to do today. It just saved me about 3 lines on a Docker file. Now, we're going to go into the exploration. So we have a general goal in mind, which is we want to take OpenSSH and try and pull some information out from it. Specifically, we're going to try and grab the username and the password as logins are performed to OpenSSH. This is where I'm going to deviate on purpose from my slides. I think this is much more cool if I just show you how to do all this stuff live. So as previously mentioned, we have a Docker file. This is already running on my server. You can see that we're running the sshd command, and we expose port 2222, and we forward into 22. This is just so that we can perform an SSH login like so. 170.0.0.1. There we go. So we have a little environment set up that we can kind of start our journey and figure out, well, how do you pull this information out? So right now we don't have a lot of information apart from SSH is running. So what I'm going to do is start by, for those unfamiliar with Docker, default it uses overlay.fs. Overlay.fs has a concept called merge directories. This is really the root directory of your running container. So I can do a quick inspect and grab what is really the root of that container. If I go back to Docker PS, we can see that we're running the user sbin sshd command. So I can check that out. User sbin sshd. And we can find the sshd binary that my Docker container is using. So we know what file to kind of go and chase after. But we need more information about this file, like where are the possible places that we can attach ourselves to. There's a common utility in Linux called LDD that helps you display the dynamically linked libraries of a given binary. So we can run LDD against the SSHD binary and get a feel for some shared libraries that it's using. There's a lot of really interesting stuff here. For the purposes of this talk, this is the library that we're going to focus on, libpam. Libpam for Linux is pluggable authentication modules. Given our goal that we want to get username and password out of an SSH session, it seems reasonable that an authentication module is probably a place that we should pay some interest to. So in the LDD output, we also get the absolute path to this binary. And instead of doing LDD this time, what I want to do is say, well, what symbols are available in this binary? The goal in my head is I want to be able to write a bit of code and basically attach it to a certain point in that program that hopefully handles usernames and passwords. So instead of LDD, we'll just do readelf. We'll ask it to dump the symbols. So we get a whole bunch of stuff here. I'm a little too lazy to read, so praise be grep. And we can really quickly get a fairly small subset of symbols that have the word auth in it, or you can try password. A lot of this, as you're going through it for the first time, is trial and error and discovery and just trying to think of different ways that programmers might label functions. But spoiler alert, I've done this before, so it's definitely one of these. So we can see if one of the symbols here is called pam get auth talk. And for the purpose of this talk, we're going to focus on this symbol. To get here, we've made a whole bunch of assumptions, right? We have the high-level goal, and we're trying to chase down and narrow the scope of what we're looking at. But we need some way to validate ourselves. Are we actually on the right path? Right? Before I go and reverse engineer a code base, I want to make sure that my time's being invested in the right area. So how can we do that? Well, there's a tool called bpftrace, and bpftrace allows you to attach really easily uprobes to a given binary, add a symbol, and perform a simple tracing function. So if I take the previous command, and instead of readelf, and I say that we want to run bpftrace, we want to create a uprobe on this binary at this symbol. And we're going to execute a really simple, hey, BSides trace message. And assuming I haven't done a typo, thank God, it will give us some feedback that it's attaching one probe. So this is still pretty useless, right? We're attaching to a point in the program, but nothing's really happening with that SSH session at the minute. So what we want to do is perform the action that we're trying to trace and see if that trace fires, right? That should be a reasonable signal that we're on the right path. If it doesn't, if we perform a login and that trace doesn't fire, we can exclude it from our search parameters and go look for a different symbol. So what I'm going to do now is just log in again to my SSH server. And what I'm looking for whenever I log in is that little trace message should be printed to the output, which it isn't. Classic. Okay, so I'm guessing I've attached to the wrong place. BPF. Oh! There we go. Okay, so it did print. Okay, I'm not entirely sure why that happened. Let me just try it again. Cool. Okay, so it is working. So this is thankfully enough validation that, hey, that symbol is probably going to contain the information that we want, or at least it's in the right flight path. So at this point, we can decide to invest a little more time in understanding what pam get auth talk is, understand the structure of that function, the parameters that it handles, and as part of that, try and identify where it could be handling the username and the password. So Prisby open source, you can go and clone libpam. I can print the repository here. Inside the libpam repository, we'll just do a simple search for pam get auth talk. We'll get a small set of results to look through. And it doesn't take too much effort to find it. So we can see the pam get auth talk returns an integer, and the first parameter it takes is a pointer to a pam handle t. At this point, I have no idea what a pam handle t is, right? But we can go and try and find that in the same way. So looking for a pam handle t, I can see from the first result it's an alias for a pam handle, and thankfully in the same results, I get the struct for pam handle. So here, this is the structure that we're getting in the first parameter of the symbol, the function call that we applied the trace onto. From the results, I can see that the first attribute is auth talk. It seems like a reasonable parameter that may map to a password. We can also see user. That one feels like an even safer bet that it's probably the username. So at this point, I feel like we've done enough investigation that we can go ahead and start investing some time in writing a little program that we will load onto this function call to extract the first parameter that is passed into that function symbol. So we can go and do a quick sitrep now, just to make sure we've got all our ducks in order before we go invest some time in writing code. So we started with a goal of let's go hack OpenSSH. We quickly find that libpam is a more interesting target. Our goal is to pull out the username and password as people perform actions like passwd or they SSH in. We know the symbol, and we also know that in that symbol, that function, it is the first parameter that it handles, which possibly contains the username and password. Again, spoiler, it is. Now, the approach differs. You can implement a BPF program in a bunch of different ways. For this demo, we're going to focus on restricted C and Golang. And we'll use bpf2go, which is a little helper utility from Cilium, to compile our BPF bytecode. But implementation details, I will show you guys some code here. Honestly, the code is probably the least important part of the talk. And you have the GitHub repository, Peter McConnell /whispers, if you want to just pull it and read through it yourself. Alright. Implementation time. We have a game plan. What are we going to do? So the first task is to build our BPF program. And it is surprisingly simple. So this struct definition, the eagle-eyed folks out there may notice, is a literal copy and paste of the last piece of code that we were on. The reason we need this is that whenever we load our program in, we have to understand the structure of that parameter so that we can read properties out from it. The struct above is simply the event that we're going to store these username and passwords into. For fun's sake, we'll also store the process ID and the command name, just so that we can see if the username and password was linked to SSHD or passwd or FTP or whatever it was. The actual C code is pretty light, right? We're down to 54 lines here, and this is all the C that's in the project. We have what's known as a BPF map, which is data structure for BPF that allows you to pass data easily between system space and user space. And we'll use this BPF map to store those events into that have the PID, the COM, the username, and the password. We then have a BPF section defined, which is our tracing function. I'm not going to go through this line by line. I'll just call out the highlights, even though there's not too much. But really all we're doing here is saying, get me the first parameter of the function call. We get the username and password address, those properties of that first parameter structure. We then read the username and password from that address into a structure that we can then put into the BPF data structure, which in our case is a ring buffer, a very popular data structure for BPF programs. And that's basically it for the C. All we're really wanting to do here is say, hey, whenever I'm called, whatever I'm attached to, get me the first parameter, try and read the username and password, and store it into our custom event object and put it into the BPF program. So we have a BPF program, but what do we do with it? How does that get attached to the running process that we want to target? For the demo sec, I chose Go. You can choose C, C++, Rust, whatever you like. It doesn't matter terribly. I'm not going to get into too many holy wars about that one. So I wrote a really simple CLI. The idea is I want to build a tool where anyone can just run it and pass in a custom symbol name or a custom path to the binary. So this code is not terribly interesting. I'm going to jump over to the listen method. Which is where most of the interesting stuff happens. So this code is a little longer. We're at 90 lines, still not terribly much. The reason why this doesn't take a lot of code is, in this instance, I'm using BPF to go, which handles compiling the C into BPF bytecode, but it also generates a bunch of helper functions in Go that we take use of here. So the likes of load BPF objects, this function here is not something that I define myself. We just got it for free as a result of BPF to go. I don't want to talk too much about BPF to go, but for the curious to see where it's being called from, this is the build file that we're using for the project, and you can see that we run BPF to go for our program. We pass in the path to our BPF code, and it generates the Go. So what we are doing here is saying open the executable, the idea being that we have a path.libpam.so.0 file. So we want to pass that in as a parameter to our function. And here we're just saying to open that executable so that we can start attaching our program to it. Once opened, we add a uret probe. So uret probe hooks into the response of a userspace function. There's also uprobe, which is the entry point, and you also have kprobes and kret probe. You can see that the uret probe is taken in a symbol. This is from a CLI arg. In our case, this is pam get auth It also passes in the program. So you'll note that at no point in the code above this did we generate this object trace pam get auth just to help map these things together. This is also generated by BPF to go, and you'll see an annotation here that maps to trace pam get auth. And for the eagle-eyed out there, you may remember that this is the name of our C function, trace pam get auth. So hopefully that dispels a little bit of the magic. So we've opened the executable, we've added the uret probe, and now we just want to read from the ring buffer that we created in our C program. So a little further down here, you'll see there's a go routine with a loop that's just constantly trying to grab as much data from the ring buffer as possible. For every event that we read off that ring buffer, we need to be able to parse it, right? We don't yet understand the structure So the way that we do that, oh, didn't like that. Crikey. Let me try that again. The way that we do that is, again, through BPF to go. So we have, let me open up, I believe it's in utils, the simple parse event data that takes a slice of bytes. And all we're doing here is reading the bytes into a data structure that we can understand in Go called event T. If I open up our types, you can see that event T is a very simple struct. But the important thing to note here is the data structure of this struct is identical to the struct defined in our C program, because we need to be able to know the size of each attribute of that structure in order to read it. So if you get really weird jargon back in your BPF program, it's likely that there's a mismatch between your Golang or your user space structure and your C-based structure. So once we get the event back in a format that we can read, we just print it to the screen. So to recap there, I appreciate there was a lot of steps, but we created a user space program. We used BPF to go to act as our BPF compiler. It took in that uprobes that we started with, it generated some BPF bytecode, and it also generated a bunch of Go helper functions that allows us to really quickly build these little applications in about 100 lines or so. And we print the result to the screen. Now for the fun part, seeing it in action. So we can go back to the previous command, which already has the path to our libpam that's running inside our container. Take this, and let's validate that it is still running. Everything looks good, and we can still log into it. 127.0.0.1. If we specify the right port. Cool. So we have a functioning SSH server ready to go. What we're going to do now is run our user space program and point it at the libpam that's currently being used by that SSHD binary, in the container. So we compile our program, which is called Whispers, just some a goofball and figured that was a cool name for it. And we will specify a binary path. We can also optionally specify a symbol. A symbol has a default value of pam-get auth-tuck. But we can see our user space program is now blocked. It's waiting for information from that ring buffer. If you remember back to the C, we only publish events into that ring buffer whenever we receive them, as you would expect. So the next part of our test is to try and validate that we actually get the data that we want. So to do that, we're going to just do another login. And if everything's done right up to this point, and I've done a login, I should be able to see the username and the password. The demagogues have been kind. So because we have written a program that targeted libpam and not OpenSSH, we also get some extra things for free, right? This is a shared library that is used by many different processes. So even though we didn't go after password, let me just change this to BSides. The exact same user space program also captures username and passwords for other commands on the host because we're actually injected into the libpam process. So that, at a high level, is essentially it. Thankfully, it went relatively smoothly. As mentioned before, you can get all the source code for this project at my GitHub. I also have a website called petermcconnell.com. The most recent blog post covers a lot of the same material, if there are any gaps. That is it. Any questions?
Is it possible to extract MFA token too, if MFA is set up on SSH?
I'll give a really generic answer to this. So The way that the probes work is you need to have privilege permission on the same system that the running process is on. So if you have any function in either user space or a kernel space that handles the data that you want to extract, then yes, you can pull it out. But so one of the questions that I predicted I would get here is like, would this apply to SSH keys, which is roughly in the same kind of ballpark as what you're asking. So in that model, we've hacked the server here, right? That's the target where libpam is running. For private keys, for example, the private key never leaves the client. You're not sending it up to the server. So as long as you're running on this privileged on the same machine where the sensitive data is being read, you can see it. If you're running on a system that never gets that file, you're pretty safe. Thanks. No worries. Yes? Exactly. So the question, if I heard it right, was given the privileged permissions that you need to load this program, does that kind of invalidate the need? So I need to be a little careful here. What I didn't show you today is you can extend this idea with kprobes. So kprobes is a very similar idea, but you're hooking into kernel level functions. So you can hook into the likes of execv or fork, and you can filter based on the command name, for example. So we could use kprobes for this exact same demo where I passed in bin path and I invoked the whispers binary. You can replace the need to manually do that entirely by having one program that listens for kprobes.
Sorry, I said you just replace libpam.sl with your own version. But I guess, yeah.
Oh, you mean like if it's a different version of libpam? Yes.
Yeah.
Sorry. Gotcha. Yeah. So so you need to have. So there's like version compatibility issues here, right? If you change the structure of that struct pam handle, for example, you're no longer going to be able to read the data. So we hard-coded the definition for that struct. Another approach is that you can try and find the header files on the VM that you're running and use that, which gives you better version compatibility. Or you can also take the approach of not using dynamically linked libraries, stripping your symbols. There's a lot of ways to avoid it. Hand in the middle. So if it's running inside the VM?
Yes.
So it should just work for free. Yeah. To get information about the host? No, it would need to be running on the actual host system and not the VM. Any other questions? I have no idea how, but I did it on time. Thank you very much.